Welcome back, students. Today we are going to see the most important and the interesting aspect in the current electricity, which is Kirchoff's law. The Kirchoff's law is the most important topic as far as the exam, the competitive exam perspectives is concerned. Okay, there are lot of questions that have been already asked based on this Kirchoff's law. Actually, there are two laws that comes under this. One is the current law. One is the current law and the other one is voltage law. So now we are going to see what the current law really does, and then we are going to see what the voltage law really does, and we are going to put everything together, and I am going to show you how to solve a problem based on this. Yes, to start with the current law. What do you mean by the current law? This law is completely based on the currents that are moving towards the junction, and that is the reason why the current law is also known as the junction rule. What do you mean by the junction rule, by the way? The currents that are moving towards the junction will take a positive sign, and the currents that are moving away from the junction is going to take a negative sign. You might wonder why the currents that are moving away from the junction is going to take a negative sign. Because there, to solve this particular junction, we actually require a current that is negative in sign. For example, you see here is a junction and there are multiple currents that are going through the junction and that is going to come through the junction. I will call this I1, this is I2, this is I3 and this is I4. Now if you just see this particular junction, I1 is going out, I3 and I4 are going out too, but I2 is the current that is coming towards the junction. So the current law goes like this. The algebraic sum of the currents that are meeting at the junction is going to be 0. What does it mean, by the way? It means that I1 plus I3 plus I4 minus I2 is equal to 0. So all the currents that are going out of the junction took the positive sign, and the current that came towards the junction took a negative sign. On adding each and everything, we end up with 0. That is what your current law exactly means. So in order to solve this, we mandatorily require a negative sign. So now what I can just do is, to solve it, I1 plus I3 plus I4 is equal to I2. This is what is done really. This is what is done really with this junction rule. This is very easy and simple. Not much is going to happen with this, because whenever you see the current that is going out, that will take positive. Whenever in some particular common junction, if the current is going to come in, it will take a negative sign. Simple as it is. Now next comes the voltage law. Voltage law. What do you mean by voltage law? Voltage law is nothing but very easy. You see, first I will define it, how it goes. The voltage law is nothing but the algebraic sum of the product of the current and the resistance. The algebraic sum of the product of the current and the resistance and the EMF in a closed loop is equal to 0. I repeat, the algebraic sum, that means you are going to sum. What are you going to sum? You are going to sum the product of the current and the resistance and the EMF in a closed loop, which leads to 0. Okay, maybe right now this might not make any sense for you, but as I go along with this lecture, you will get to know how exactly this thing works with the voltage law. Very important, listen. So before I could explain this, before I could explain the statement, it's better I explain you about the sign convention. Okay, you please bear with me. Just at the beginning, you might not be understanding how the whole thing works, but as it goes along, when I start doing the problem, you will definitely get to know how the entire thing is going to go about. Yes, sign convention. Yes. What is a sign convention? Listen. Here is a resistance. Observe very carefully. Here is a resistance of resistive value R, and let's assume that the current is going this way and the current is going this way, and if you try to walk like this and you try to walk like this, the potential V is equal to it should be minus I into R, minus IR. V is equal to minus IR. And now here is the resistance, here is the current I, and if we try to walk it opposite to the direction of the current, the V will take a positive IR. So listen, whenever you walk in the direction of the current into the resistance, you get a negative sign. Whenever you walk in the direction opposite to the current into the resistor, it is positive. Right now it might not make sense, please bear with me. Now again, like this, if you walk into the positive terminal of the battery, if you walk into the positive terminal of the battery, it will take a negative sign. It is negative V. Now, if this thing goes to the negative terminal of the battery, if you walk through the negative terminal of the battery, this will take a positive sign. Okay, this will take a positive sign. Likewise, there are equal things for the capacitors also. Here is a capacitor, plus minus. Here the capacitor is plus, here the capacitor has got a negative sign. Here the plate of the capacitor is going to carry a positive and there is negative. If you walk into the capacitor this way, it is nothing but minus C, which is equal to Q by V. Likewise, if you walk into the capacitor in the negative sided plate, it is positive C, which is Q by V again, right? Here you will get a negative sign. This is how the things are going to really happen. This is the rule that I will be following throughout the problem. Yes, now I will directly give you a circuit, I will draw a circuit and I will show you how the sign convention is actually applied in there. So here is a resistance, and now there is a resistance again in here, and here is going to be a battery, and it comes around in here. Here is again a battery, here is again a resistance. From there you again get, from there it again extends and you get a battery down here. Again you get a battery in here which is connected down to this. Okay, so what I am going to do is I am going to first name the resistors and I am going to name the currents, and accordingly I will start doing things. I will call this E3, I will call this E2, and I will call this E1. E1, E2 and then E3, and now the current that is going to go this way, it is I1, and then it goes up, this is I2, and then the current will come out this way, and again the current is going to come out this way. So this is I4 and this is I3. So this is a given circuit. The circuit might look clumsy, but this is a closed circuit. You might wonder, what are these vertical lines? These vertical lines are the extensions of this circuit. Okay, no problem. So this is a given circuit for you, and the very first thing that you have to do whenever you come across a circuit or to solve a Kirchoff's law, you have to distribute the directions of the current. That is the first thing that you do. You distribute the currents depending on the directions. Sometimes even if you go wrong in distributing it, or sometimes it is very difficult to distribute it, instead of knowing the potential of a battery, it will be difficult for you to distribute the currents, but still it doesn't matter, it will be good. The very first thing that you have to remember whenever you are solving it is, choose a junction from where you will start to walk. Second, you walk either in a clockwise or in an anti-clockwise direction, but that should be conserved throughout the problem, which means if you start walking in an anti-clockwise direction for a loop, and for the other loop you should not walk in the clockwise direction, that will go wrong. So whichever direction you start to walk, that direction should be preserved throughout the problem for all the loops. Yeah. Next, the Kirchoff's junction rule should be preserved. Okay, for all the junctions, Kirchoff's junction rule should be preserved. Okay, and always choose to go with a junction which at least has one battery with it. These are the few things that you should always remember whenever you start doing a problem using the Kirchoff's law. In this particular problem, what I am going to do is, I am going to start walking from this point A, and I will go around, I will again come to this point. I am going to walk in the clockwise direction. I am going to walk in the clockwise direction. Ready? So first from here I go to this resistor which is R1. I will call this resistance R1, this is R2, this is R3 and this is R4. So starting from A, walking clockwise, I walk into the resistance R1. When I walk into the resistance R1, I walk in the direction of the current. If you could recall, what was the sign convention? If I walk in the direction of the current into the resistance, it takes a negative sign. So here it takes a negative sign, minus I1 R1. Then I walk into this resistance which is R2. Into this R2, what happens? The I2 is going in the opposite direction. I am walking in the clockwise direction. I am walking in the clockwise direction, but that resistance is actually has a current in the opposite way. You see the red color lines that I am indicating are the directions in which I walk. So I walk into the resistance in this way, but my current is in the opposite direction. So what did I say? If I walk in the direction opposite to the current into the resistance, it will take a positive sign. So positive I2 R2. Again I continue walking. I enter into the positive terminal of the battery. What is the sign convention you get when you walk into the positive terminal of the battery? It is negative E. Minus E1 it is. Again I continue walking. Again I continue walking. I walk in the direction opposite to the current into the resistance R3. So it takes a positive sign. So positive I3 R3. Again I enter into the positive terminal of the battery, which eventually takes a negative sign, which is minus E2. And then I continue walking. I walk into the negative terminal of the battery E3. So that takes a positive sign, which is positive E3. And as I continue walking, I walk in the direction of the current. I walk in the direction of the current into the resistor R4. So it will be a negative I4 R4. The whole thing equals to 0. This is what I was talking about in the statement. What did I say? The sum of the product of the current and the resistance and the EMF in the circuit is equal to 0. I repeat, sum of the product of the current and the resistance and the EMF of the battery will be equal to 0. So I added each and everything, that goes to 0. That goes to 0 eventually. This is how your Kirchoff's law really works. This is how your Kirchoff's law really works everywhere you see. Okay? You choose a junction from where you start to walk. You walk in the direction of the current into the resistance, it is negative. You walk in the direction opposite to the current into the resistance, it will be positive. If you enter into the positive terminal of the battery, it is negative. If you enter into the negative terminal of the battery, it is positive. One thing, you choose a loop and you start walking. You never walk in an open circuit. Okay, you should always choose a loop and you should walk accordingly. So these are the few rules that you have to keep it in your mind all the times when you go and solve the Kirchoff's problem. Clear? So these are the few applications of it. So with this note, in the next section, I will individually take a problem and I will solve using Kirchoff's voltage law. With this note, I will stop here today. Thank you.